Hi guys, welcome back to Data Every Day. So today we're looking at a data set of personality types of different people who have posted um, some sort of text online. And what we're going to try to do is classify whether a given person is an introvert or an extrovert, or at least whether they're exhibiting signs of introversion and extroversion based on what they've posted. So let's get into it. I want to note before I start this video, I'm going to turn on GPU acceleration because we will be using an RNN today, which take more time to train than standard dense layer neural networks. So it's a good idea to have GPU acceleration enabled. Alright, so we're going to use TensorFlow RNN. More specifically, I'm going to be using a bidirectional GRU to make the predictions. So here I have some imports, NumPy and Pandas, just for processing the data. I'm going to get stop words from nltk.corpus. So this is just a list of words that are not useful in making predictions. And then we'll be getting a tokenizer and pad sequences function from keras.preprocessing for transferring the posts that people have made into sequences of unique integers. And then we will get the train test split function from sklearn and use TensorFlow to build our model. Let's go ahead and import those, and we can load in the data using pandas.readcsv. Pandas.readcsv. And then get the file path right over here, copy the file path, paste it in, and load it in, and then we can take a look. So we just have two columns, our type or label column and our posts column, which is going to be what our inputs that we're going to try to use to predict the type. Now there's actually 16 different types in here. I tried running a model that predicted one of 16 types. Couldn't get more than 40% accuracy or so, and it looks like other people on Kaggle got around 25% accuracy. So it seems like a very difficult task. I decided let's go with something a little easier. Let's just try to predict if there's introversion or extroversion present in a given example. Let's just get a little information about the dataset with data.info. So we can see there's no null values and just two columns, both of object type. So with that, we will proceed and start preprocessing. So I would like to I'd like to get all my preprocessing out of the way in a single function. So I'm going to create a function called preprocessInputs that's going to take in a df, or data frame. And data frame will always take the form of this, so I'm going to split it now into texts, which will be just the posts column. So not tf, it should be df. And I'm going to make a copy of it. And our labels, which will be just the type column. Make a copy of that. Alright, then we'll process the text data. So the first thing I want to do is I want to just apply a few pretty basic filters to the examples. So let's take a look at this. Let me just see, we do data.loc, so the 0th row and the first column. Actually, it should be like that. Oh, actually, iloc. Whoa. Oh, this is it. This is the text that the person posted. Yeah, wow. So it's pretty intense. Luckily, our tokenizer, this thing we're going to import from Keras, has a lot of built-in filtering mechanisms already in it. So all the punctuation will be taken care of. All I'd like to do is try to remove some stop words. So what I'm going to do is get our stop words. This comes from stop words. This I imported from the Natural Language Toolkit. .words, and we specify a language here, English. And then texts, which is just a list of a bunch of these things. Texts will become a new list with values from texts. Actually, we're going to apply transformation for every text in texts. So for every text in text, we're going to make text equal to text.lower. So originally texts is a panda series, but it's going to now be a list consisting of lowercase versions of the text for every text in text. Then we'll do a similar thing, except this time. So it's going to be very much the same, except instead of lowercasing it, we're going to split. So now each string is going to become a list. So we'll have a list of lists. Now I'm going to apply some word-wise transformations. So each list in text is going to be a list of words. So if I have this, let me do it this way, for text in text. So this is what I was doing before. I'm applying something to text for every text in text. But the thing I'm applying now is actually going to be a word-wise transformation for every word in text. You see? So here I'm applying transformation for every word in text, and outside is being applied to every text in texts. Hope that's not too confusing. But what I'm going to do to each word is first I'm going to strip the white space. So it's going to strip each word for word in text, and we're going to do that thing to every text in text. And then I'm going to do another one, but instead of stripping the white space, I'm actually just going to keep all the words that are not stop words, if word not in stop words. So we're going to, for every text in texts, we're going to apply a word-wise transformation for every word in text, but only keep the words that are not stop words. So we're essentially removing stop words with this. Okay, then I'm going to specify vocabulary length. So we could use all possible words in all possible texts as our vocabulary length, but I tested it and there's about 400,000 different words, and that can actually decrease the performance of the model. So if we limit that to a fixed value, how about 10,000? That seems to work a lot better. And in most cases I found that is the case. So let's create a new tokenizer object, but specify numWords to be vocab length. So when we tokenize the sequences now, will only be, it will just discard anything but the top 10,000 most frequent words. So numWords means we're only going to use the top 10,000 most frequent words in our tokenizer. So then let's fit the tokenizer on the texts, passing in texts. And then we're going to reassign texts to be tokenizer.texts to sequences, passing in texts again here. So we're going to take our texts, and each word is now a list of words, remember? Each word is going to go to a new, it's going to go to a unique integer given by the tokenizer. And the integers are sorted in terms of frequency. So the most frequent word will be given 1, the next most frequent word will be given 2, and so on. Then let's get the length of the longest sequence, the max sequence length. Here we can just take text in text, so just a list comprehension that recreates our text list. But instead of just doing text, we'll get the length of text. So what this will become is a list of all the lengths of each text, and then we can do numpy.max to get the longest list, or the longest sequence, and store that number in max sequence length. Then text will be pad sequences. So now what we're going to do is use this longest sequence data to pad each sequence with zeros. So we're padding texts. Max length is given by max sequence length, and we'll enable padding equals post. So what this is doing is going to, this will make each sequence the same length, and it will just pad all the shorter sequences with zeros at the end. That's what post means, so that we have every sequence is the same length. Okay. Now we're finished processing our text data, we should have a two-dimensional NumPy array of texts. And now we can go on to processing our label data. So let's take a look at the label values up here. Just looking at this type column, looking at the unique values. Okay, so here's a list of all of our labels. If I create this variable called label values, just make it like this. There's two ways I can code this. I could assign each one to a unique one, but like I said, we're only going to get accuracy of about 40% if we do that. And additionally, these are really imbalanced classes. Some of them have very few examples. So we're going to instead create a binary labeling. We'll call it label mapping. Will be a dictionary that does some mapping for a label to an integer. I'll come back and change this value. I'm just leaving it there for a second. For every label in label values, right? So we're iterating through label values, getting each label, and now we want to assign each one to a unique integer. So that's this integer here. What I'm going to make it is I'm going to check the first character of label, and if it equals e, this will be, we're going to turn this into an int, and that's going to be our value. Why not make it a NumPy integer? But basically, this will be a Boolean value, true or false. It's either e or I, right? So e will be 1. Anything that starts with an e will be 1, which is the extroverted ones. And anything that starts with an I will become 0. The numeric type conversion is being applied to the Booleans for every label and label values. So our label mapping will essentially give one of the, it'll give a label mapped to a number that will be either 0 or 1. And with that, all we have to do to transform our labels is call labels.replace and pass in the mapping. And that will just perform all of the transformations for us. Okay, then after that, one last step, I'm going to turn it into a NumPy array, just so that both of our outputs of this function are NumPy arrays. And then we'll return a bunch of values. We'll return the texts, we'll return the labels, then let's return the max sequence length. These are values we'll be using later. We'll return the vocab length, and we'll return the label mapping. Okay, there we go. And now let's just store all those in their own variables. So texts, labels, max sequence length, vocab length, and label mapping equals preprocess inputs, that's our function here, pass in data. Stop word, should be stop words. Okay, so that's going. Alright, it finished. And now let's just print out the values that we got so we know what they all look like. I'll just paste this in. So our sequences take the form of, you can see that this is the number of examples, and this is the length of each sequence, which is given by max sequence length. Our labels is just a one-dimensional vector of each example. This label should be zeros and ones. And then this is our vocab length and our label mapping. You can see all the ones that start with I get mapped to 0, and all the ones that start with E get mapped to 1. Okay, so now let's perform a train test split. So texts train, texts test, labels train, labels test equals train test split, passing in texts and labels, giving it a train size of 70%, and we include a random state of 1, 2, 3. This can be any number, just so we can reproduce the results. Okay, and then we can train. So, like I said earlier, we're going to be using a RNN, recurrent neural network here, and we're going to embed the words in a dense representation. So what I mean is, Um, we have 10,000 different words, right? We're using the 10,000 most common words. So we could do a sparse encoding where we encode each word in a one-hot vector of length 10,000. But the only problem with that is we then have a lot of useless information, all those zeros, right? So instead of encoding in a vector of 10,000 elements, why don't we shorten it and do a smarter move, which would be embedding it in a smaller dimensional vector space. And the vector, this can be any number. The one I found that works for this model is 512, works the best in my opinion. But basically, it's going to send each word, which is given by an integer. Here, I should probably show you what text looks like. It looks like this. These are the sequences of our words, with padded with zeros at the ends. And you can see each word is given a unique integer. And the lower the integer, the more common the word is. Now, each one of these integers is going to be sent to a new location in 512 dimensional space. And the benefit of that is now it only takes 512 elements to describe where in space the word is. And in addition, we're going to do this with a Keras embedding layer, with tf.keras.layers.embedding, which will actually decide where to send the word. It will learn where to send the word, right? It actually has weights that point it to a different location, so the model can learn smart or optimal ways to embed the characters, actually the words. Now, it used to be that you had to apply so many different text filtering and transformation like filters to the data, so that the model could understand in a typical bag of words model. Like, for example, URLs would have to be completely taken out. However, with this embedding form, it's really not that important, because the model can learn that all URLs are sort of the same thing, and it can send them to locations where they sort of mean something together. Right. So we don't have to do a lot of the pre-processing. I only did some minimal stuff like taking out the stop words. I'm not sure if maybe some more processing would affect the performance. But let's just go ahead. So first I'll have an input layer. That'll just be, not actually layers, tf.keras.input, and specify the shape. Each input will be a vector of length max sequence length. And inputs. I also want to note that I had a typo earlier. I called this len instead of length, so I just fixed that. Okay. So we have our inputs, and we're going to feed the inputs into embedding. But now embedding needs a few arguments. So we have to specify an input dimension. This is sort of the dimension of a one-hot encoded word. If we were to one-hot encode the word in a sparse format, this is the dimension of that, and that would be our vocab length, 10,000. And then it's going to transform that to a dense encoding in the dimension of our choosing, which is embedding dimension. So output dim equals embedding dim. Okay, and the last thing it takes is the length of a given sequence, which is given by input length, and that's just our max sequence length. Okay. So now that we've embedded our words, we're going to feed it into our GRU, gated recurrent unit. This is a simplified version of an LSTM, but it tends to perform better on smaller datasets. So let's not just make it a regular GRU, which is given by tf.keras.layers.gru, but let's make it a bidirectional GRU. So a bidirectional GRU will take input from both the past and the future. So if you're not sure how recurrent neural networks work, I recommend you look it up. It's really interesting. Basically, it takes as input a new word, but also the word from also the last word, right? So it has a sense of memory. It loops. It feeds in the output to the next input. However, if we make it bidirectional, so we wrap it with a bidirectional layer, this will create sort of like two GRUs, where one is taking input from the past, the last word, and the other one feeds the sequence in backwards and takes input from the next word in the future. And this can give a model a sense of context greater than just looking at the past, right? In cases where you have access to future words, like in this case, right? In this case, when you're reading someone's post, you can see the future words and the past words simultaneously, whereas in some sequence problems, like for example stock data, you wouldn't know the future, so you could only use past data. But in this case, we can use both, so we're going to use a bidirectional. And the GRU is going to take a number of units. This is just any number. The higher it is, the more prone to overfitting, obviously. More parameters. I believe 256 works well here from my experiments. And we're going to enable return sequences. So return sequences means it won't just return a single output after the full sequence has been passed through. It's going to return the output at each time step as a two-dimensional matrix. So this actually will output a two-dimensional NumPy array, or actually a tensor. So here we'll pass in embedding. And then because this outputs two-dimensional tensor, we're going to want to flatten it with a flatten layer. tf.keras.layers.flatten, passing in GRU, and then we'll have a one-dimensional vector, which we can then feed into our outputs, which will just be a fully connected or dense layer with one activation, because this is a binary classification problem where we either have a 0 or a 1. So there's only one activation, which will be the probability estimate of the positive class. So how likely is an example to be an extrovert? And that is going to have a sigmoid activation, so that this takes a value between 0 and 1. Alright, then we'll create our model, tf.keras.model, pass in the inputs and outputs, and then we'll compile the model. So we're using an atom optimizer. For loss, will be binary cross entropy. And our metrics, we'll use accuracy. We'll also use AUC, which is better at dealing with class imbalance. Give it a name as well. I would like to see how imbalanced our classes are. So labels is all of our class data, and we're really only concerned with labels train. We can take the mean of this to get the class distribution. Since it's zeros and ones, we can do that, because it sums up all the ones and then divides by the length, which is just the same as saying what percentage are ones. And it's 23% ones, so it's a bit imbalanced, actually quite imbalanced. However, I seem to be getting some decent results with this. Let's see how it goes. So then let's train our model, and we'll store its train history in history, model.fit. So we're going to train it on text train and labels train, and then we'll give it a validation split of 20%, batch size 32. These GRUs tend to train for short times, even though each epoch takes a while to train. Only a few epochs is required, so I found about 5 epochs is good. And let's train. Oh, I must have not passed something in properly. Inputs goes to here, embedding goes to here, GRU goes to here. Flatten did not go to the outputs. Okay. So we'll evaluate the model when it's finished on the test set. Text test, labels test, labels test. And I will resume the video when it is done. Alright, it has finished training. And if we go ahead and evaluate it on the test set, we end up with an accuracy of about 80.5, 80.6%, and a AUC of about 0.78. Now, I noticed that on our first run, we have a higher AUC, but a lower accuracy. And this may actually be a better model. We may want to go back and retrain for one epoch, or use a callback like save model checkpoint so that we can save the weights from this one and load them up after. But more or less, this is a pretty good performance. And that will sum up today's video. So thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.